Hello, hello. Hello, everybody. One second as my board comes in. Hello, hello. One second. Please bear with me. Yes, okay. Okay. Hello, hello. Hello. Wait, the board is good afternoon. All right. I will hold on. I know my head is not. Okay, here we. Okay. 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 All right. Hello, Annie. Hello, Yanelli. Hello, Chastity. Hello. Hello. Oh, that was voice. That was voice. That's points right there. But she knows that already, and most of you know that. Hello. Okay. Hello, Vanita. Hello. And now that's okay. That's people. And now the chat. Hang on. Yes. Hello. Good afternoon, Ella. Good afternoon, Genesis. Good afternoon, Yanelli. Good afternoon, Chastity. Oh, did I say I said Chastity? Sorry. Good afternoon, Sydney. Good afternoon, Vanita. Good afternoon, Kaya. Good afternoon, Brian. Good afternoon, Natalie. I know we went through this before. I think
Yeah, it's Natalie.
it's Natalie. All right, it's exactly what I right. So I'm double right. Okay, thank you. Thank you. Sorry about that. Okay. And that's voice. That's points right there. And she we can count that as correcting the professor respectfully. So there's like many points you can get for that. Just look for the portals. Okay. Good afternoon, Ariana. Good afternoon, Carlos. Good afternoon, Gabriella. Hi, direct chat person. Okay, who else do we oh, and Kaya's got the animated avatar going. That's points right there. That's awesome. Vanita and Chastity have the avatars that are not animated going. That's points right there. Gabriella and Annie have the videos going. That's points right there. That's awesome. Who else? Did I say Vanita? I said Vanita. And hello, Emanuela. Welcome back. Hello, Mariam. Hello, hello, Brandon. Who else did I not say? Okay, I think that's everybody. If I didn't say your name, oh, Mariam. Yes, good afternoon. Awesome. I think I've said everybody's name. Okay, so we're gonna get rolling in a second. Again, we're in that stage. Like I've had many of you before, but I've had many of you not before, or I've not had many of you before. So it's a little bit of a balance. I mean, in terms of like how the class is run and the points and all this participation madness and everything, like I'm trying to strike a balance. I mean, for those of you, I don't want to over talk about it or talk about it too many times. But any of you that I've not had before, like hopefully you're getting used to it or understanding how it's working. But please feel free to email me or text me or even put in the direct chat if there's something unclear about like the grading or how the points work. Please let me know, even if I don't want to make a big explanation again in the middle of class at the risk of boring other people. Like, I don't think it is entirely clear. I don't see how it could be entirely clear to all of you. So don't be shy about like how the points work or how the participation work. Don't, you can even put it in the chat and eat. Okay, just let me know if you want me to explain it more, even if I explain it, one on one. Um, and obviously, as I try to just sort of remind people as we proceed about how you're getting points for what. So, I mean, I'm going to get to the physics homework in a minute, which um you guys did very well on so far. We'll talk about that. Uh, but yeah, but as a reminder, all of these points, anything that has come up so far that is not an exam, which is everything that's come up so far, anything that's not an exam, it's all for points that help your grade, that can substantially help your grade, but it is all optional. Like, I mean, I would really recommend that you do the homework. I mean, it's like a really bad idea not to. But just to be clear, if you all these game things and participation things, if you don't do them, you don't get zeros, you don't get penalties. It's nothing like that. Same thing if you don't show video or you don't say hello or you don't, you know. use your voice to participate in the class. You don't get zeros or penalties or anything like that. But anything you do that is that helps you participate and engage, there's various ways to get points for the fact that you did it. Just like that's the bottom line. So it hopefully becomes clearer and clearer every day. But let me know if it's not. I'm just looking. Who else? So hello, Samantha. Welcome back. Hello, Skylar. Welcome back. Who else did I not say hello to? Okay, I think that's everybody. I think so. I want to. So again, yeah, just stop me anytime with questions. And if you're shy, if you think it's going to drag the whole class down, put it in direct chat, and I'll make a decision. Um, but what we're here today mostly to do is just start walking through going over homework one. Number of things to say about homework one. I have a number. Well, I'm gonna okay in a minute. I'm like literally I'm gonna share the screen and start going over how I did problem one of homework one, what it is I'm looking for from you, what you would need to do to get all of the points. Like I will walk through that in a minute. I'm not going to walk through every question of every homework set of every day, but certainly this week I am. Um, so let me make a couple of things clear. First of all, there's absolutely no way we're going to finish going over homework one today. We never go over all of homework one in just one class period. So I just want you to be aware of that. I'm going to go overly slowly at first, telling you I'm going to drag out all the details of even the very first question so that we're all on the same page of exactly what I'm looking for with the with problem solving in this class. So please forgive and indulge me. Then we will start speeding up more and more. So even at the end of today's class, I'll probably just like blurt out what I think the answers are to question 2, 3, 4, 5. Will I do that? Yes, I will do that. I will like say the answers to question 2, 3, 4, and 5 so that you have perspective on how you're doing or whatever. And then we'll start going through those like faster next period. But today is making sure that we're super clear on exactly how to submit these problems. So yeah, so please don't be surprised or upset if we okay. So the big deal of homework one, the big deal is question nine. Like that's what question nine is what really launches us into the material of this semester of like physics 204 material. Like we get into that for question nine. Question nine is hard. I saw many of your attempts at question nine. I'll talk about that in a second. But no matter who you are, by the time we get to question nine, now we're really having to think and deploy some kind of advanced mathematics. And a lot of us got stuck somewhere at the beginning of question nine or right before question nine. Or a lot of us found things or knew things or saw things from the web or from another math class where we actually wrote down things that may have even been correct. But I asked many of us for like more explanation or justification of those. Like, even if something's correct, and it's on the web or something, that does not mean we understand it or that we understand why it's like applicable here. So for most of us, for most of what I've seen so far, we're going to need to really think through question nine. Therefore, in order to see how to do hard things that we haven't done before, I'm going to over explain how to think through things that we kind of do know how to do, which is question one. Okay, so you're gonna have to bear with me on that. Right. So, well, in fact, yeah. Let me. Is it? Yeah. I'll just so you. Okay, so get rolling. So in a minute, I'm going to start talking about question one on homework one, which is like right here, right? Um, but I also want to make super clear, especially to especially if you haven't had like if I haven't had you in my class before. So this is the deal. If you submitted a respectable first draft of homework one on time, like if you submitted it before 3:05 p.m., if you submitted a respectable first draft, which means you attempted most of the problems, you attempted to show 5 steps of reasoning for each of the problems. If it was like a thorough, responsible attempt where you basically showed that you know the class expectations, which by the way, I think pretty much all of you did. If you submit a first draft on time for a homework, then no matter what score you got or didn't yet get, you can get all the points on it. Let me be slightly more clear about that. I'm saying many of you submitted this homework not only on time, but sort of early enough, like early enough today or yesterday, that I had a chance already to go through it and already give you quick feedback in the comment section of Google Classroom and a score. If you already got some feedback and a score on your homework one, what that means is definitely you turned in a respectful first draft on time. So even if you didn't get a perfect score, which I think is true for everybody, even if you didn't get a perfect score, don't even stress about the number you got. Take the number as an indication of feedback. Like the number is telling you there's still something I need you to fix or something or improve, which I explain in my quick comment. And so, whatever it is that I'm asking you to improve or fix, you totally can and should just revise and re-upload when you get a chance. Like upload a new revision, a full revision of your homework, and then you'll get all the rest of the points. I know this is clear to some of you. I just want to make it clear to everyone. As long as you submitted the first draft on time, then you're in a position to get all the points as long as you sort of keep resubmitting. Many of you already got it back with the number. There's about 4 of you. I'm not going to name any names at the moment. There's about 4 of you who totally did do it and you did it on time. I know for a fact, like you did it on time, but it was like close enough to class. I just haven't gotten to yours yet because I mean, technically it was just due now. So there's about 4 of you. I mean, if you want to hang out after, if you're concerned, you want to hang out afterwards, I can tell you, but there's like 4 of you who totally did it. You totally did it on time, but you haven't gotten feedback yet. Yes, you definitely can get the full score on it, no question. And the rest of you, if you got any kind of feedback, just when you incorporate that feedback, make a whole new draft. Don't just fix that part. Even if your whole draft is like 30 pages long, fix whatever parts I asked you to fix, and then resubmit the whole thing of 30 pages, leaving the old one up there, and then you'll get all the rest of the points. I just want to make that clear. If there's any question about that, let me know. But that's not just true for the first assignment. That's true in general. You can always revise and upload for all the remaining points if it's worth your while to do so. Okay. So now I'm going to walk through what I was looking for. I'm going to quickly, and obviously stop me if there's any questions. I'm going to just quickly do a screen share just in case, like you're watching this later on video or something, just
I
to
have
show.
a question.
Oh, sorry. Yes, absolutely. I'm sorry. Yes. Is that Annie?
Yes. So,
Yes. Yes.
yeah, it's Annie. Yeah. So do
Okay.
we just assume that for the questions or like the sub questions that you did not comment on or highlight on, do we just assume that we got the right answer?
Yes, and in your case, yes. If I right, if I didn't comment at all, not only it's not just that you got the right answer, but that I'm totally approving everything that you're doing. Yes, and what I try to do, like, and I remember this in your case, but in general, in people's cases, like, then I try to summarize in the comment section of the Google Classroom. Like, if I say like beautiful work in general or whatever, I mean it. Like, yeah, that everything was fine, totally more than fine until I hit some kind of issue. So yes. And in your case, I know that's right. That yes. Um, right. So that when you submit a new draft, you could just literally read just you don't have to change those pages, just change the pages that I said something about and then put it all together and put yeah. Okay, but good question. Wait, other questions like that? Is that um so yeah, by the way, I hate that. I don't hate the question, but I that actually annoys me to like that to not get compliments and just get criticisms. I'm going to try not, but I'm actually trying this semester to all of you. I'm sort of would rather be fast with these things than get bogged down and then fall super behind like I did last semester and that I sometimes do. So yes, if you don't get a critique on something, assume it's good, and then I'm happy to compliment you in person or whatever. But I'm sort of going for speed this time. But yes, okay. If there's no other questions for the moment, you can ask questions anytime. I'm just going to switch the screen share for a second, just in case you're watching this later on a video or something. Oh, I just lost it. Hold on. Hold on one second. Right. What happened? What happened? Try that again. Right. Okay. Okay. So just for posterity or whatever, this is what we're about to go over. This sheet, right? This situation where we have a mass on a spring. In principle, by the way, in principle, most of the questions, so this situation, you have a mass on a spring, it's held out to a certain initial position. It's going to be let go from that initial position that is not the equilibrium position. The equilibrium position of the spring we call x equals 0. So then we're going to ask a bunch of questions about what happens to this mass once it's released from a non-equilibrium position. Just to be clear, most of this situation and most of these questions in principle is like classical physics stuff. In principle, this is like review or recall or transition from physics 203, which doesn't mean that all of you feel completely in command of these questions. It doesn't mean that you did it in detail in physics 203 or something like that. I mean, depending on who the instructor was, including me, like you may not have thought this through in detail. But this material, questions 1 through 8, is the material, the topic from classical mechanics. And we're building the new material, the new physics, physics 204, from this. You'll see why by the time we get to question 9. I mean, the first sort of chapter or the first chapter or topic of physics 204 is called oscillations, or more particularly harmonic oscillation. If you want to follow, I always forget to say this, if you want to follow or reference any of this, like in the recommended textbook, it's chapter 16. I'm 99% sure. It might be chapter 15. I always get them confused. It's either 15 or 16, but it's the chapter on simple harmonic oscillations. Okay, that is the first topic of physics 204. It's uh so this investigation of a mass on a spring and these early labs that you're doing, or the lab that you already did last week, transitions us from old classical mechanics to oscillations, wave propagations, and fields, which is this course. I'll be more detailed about that next week. Like I'll try to put it all in perspective for you. But just so you know, in theory, questions 1 through 8 are kind of like old material, but then question 9 is where it blasts off um into the new topic here, right? So okay, so this is the sheet that we're going over, right? Now I'll go back to the other. So we're going to start walking through it now. And yeah, and the very first question that we're going to ask is, with this mass that's sitting on this spring at 15 centimeters from the spring's equilibrium position, it asks right away, what is the force? It's asking what in newtons, what is the force exerted by the spring on the mass at the instant that it's released? Now, that's the first question, right? The one on the screen here, number 1. I'm going to say right now, the answer to that question is is F equals negative 30 newtons, or put more explicitly, at x equals x naught, or you could say at t equals 0 seconds, F equals negative 30 newtons. Now that's the answer. That's the answer, just to get that out of the way. So if you got that answer, like cool, then good, you're with me. Like we're on the same page. Now I'm going to bore you to tears. I mean, I don't want to, but I may potentially, if you got that answer, I'm now going to talk for like an hour, not like 45 minutes, and break down that answer. And if you're anything like me, if you're anything like the way I was in college, you may be sitting there going, I cannot believe this. I cannot believe he's spending this much time talking about an answer that I see in my head. Okay, I want to warn you in advance. And again, I've warned some of you of this before. I totally respect the fact that you can do that in your head. I get it. And probably that question, probably I could do it in my head too in college, maybe. Um, but the reason I'm going to talk so much about exactly the steps I want you to show of getting that answer is because I don't think that we can do question 9 in our head. I don't think any of us can. And I think question 9 is just the beginning of what's about to happen in this class. I think we're going to very soon get to questions that not only can we not do them in our head, but we really don't know where they're going or where they're going to land. Like we can't even envision the kind of answer that they're looking for. We're going to get to questions where some of us, like me, would look at the question and go, I really don't even know what you're asking me or what you expect me to do. Or we're going to get to questions, and I think question 9 is one of these kind of questions for many people. We're going to get to questions where we say, all right, yeah, like, yeah, I guess I understand what this is asking. I could even see maybe why it's fair, but honestly, I don't really even know how to begin this, right? That's going to happen to all of us if we're challenging ourselves appropriately, especially in this class. We're going to get to questions where even if we sort of have been doing everything responsibly, where we don't know how to begin. So I'm here to tell you that the way to begin a question when you don't know how to begin is to do the 5-step method. The 5-step method is the life raft for what to do when you're out at sea and you don't know what to do. And the only way the life raft works and saves you from a situation where you really don't know what to do or you think you don't know what to do, the only way it works is if it's been unpacked and practiced in situations where we did know what to do. Like honestly, so I'm a little defensive on this, as you could tell. I don't mean to be defensive, but like I'm now, since we all, I think, know, or many of us know that the answer to question 1 is F equals negative 30 newtons. I'm now going to show you the thought process I believe that actually did happen in your head, even when you did it in your head and you thought it just came to you. I'm here to argue it didn't just come to you. Moses did not come to you in a dream. Jesus did not come, and I'm not saying this mockingly, but like it wasn't a spiritual epiphany when you saw negative 30 newtons for question 1. It's that you're smart, and I'm smart too. You're smart, so your brain did a bunch of steps super fast, so fast that you didn't think of them as steps. You just thought you knew. So, what we want to do right now is break apart those steps and see the steps that our brain does when it knows something. And it's those steps that we want to repeat when we feel that we don't know something. And in particular, I promise, I'm going to shift the screen, I'm going to get going. But in particular, it's steps 1, 2, and 3. That is what people always skip even when they think they're showing work, or even when they think they have a method for like doing science or math problems or physics problems, people, I know you're all used to showing work. I get that. And you're used to like doing a lot of computations. But whenever we ever look at a physics problem and go, I mean, I could do that. I think I could do a lot of it. I do this, but I just don't know how to start that one. I need help starting. What we're really secretly a lot saying without realizing it is we can do the math. We just don't know how to set up the physics that leads to the math. And what that really means is we can do step 4 if someone starts it for us, but we don't know how to start step 4. And the answer is do steps 1, 2, and 3. Like really. You'll see what I mean. All right, so I'm gonna so please bear with me and listen, even if this seems really annoying and overkill what I'm about to do, it's for the sake of knowing what to do when it's not clear or overkill. So I'm gonna switch the screen. Wait, hold on. Or did I admit the person in the way? I think I did. Okay, I'm going to switch the screen. I'm going to switch the screen. Okay, right. Okay, 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 okay. So, all right. So here we are. Homework 1. First thing, and again, forgive me if I've said this. First thing, you notice how I was just on one screen and like it was showing the problem, and now I've switched to a different screen and I have a blank document that doesn't have the problem copy and pasted into it or anything like that. That's what I want from you as well, especially those of you that I've never met before last week. Like, please, and actually, I'm saying all this, but actually, your homeworks were amazing, by the way. I'm saying all this, but I really don't need to say all this to this group because even though, again, with the exception of like 4 assignments that I haven't looked at yet, all the homeworks I saw, you actually really were doing all of this. I'm going to stop oversaying it because I think you all do get that I want a self-sufficient document on separate paper that speaks for itself. It's actually your homeworks. So yeah, your homeworks were actually quite impressive. Can I just say that definitively? Really, all the ones that if you got back homework from me at all with any number on it, please know that I actually was like, whoa, for our first homework, this person really knows what I'm looking for. Wow. And for most of you, you actually rocked through the whole thing and then maybe got into some challenges in question 9. I'm just realizing, and I mean that about your section in particular. Like, I don't actually always have that experience on the first homework. So now that I'm remembering that, so please take the compliment. And again, no, especially if you just joined the room, if you didn't get all the points, you're going to get all the points if you just make whatever tweaks. I was asking, or you just wait till we get up to question 9 and we explain it through, and then you redo question 9 and you'll be fine. So, okay, I'm going to talk fast. So you guys know what you do. So, all right. So, question 1. First, I do step 1, DFP, as most of you did. I make my own diagram. I don't copy and paste. Little subtlety to know about the diagram. I think most of you did this, but maybe not all. Notice and now I'm going to talk faster, but that doesn't mean you can't stop me. Please do stop me. I'm just realizing that most of you don't need to hear all of this. Um, so I'm just going to address subtleties. When you do a diagram, step 1, diagram and fact pattern, the key purpose to the diagram really is that you're defining the terms of step 4. That's really what's going on. All the constants and variables, all the letters that are going to be used in the computation of step 4, they mean something, especially to someone who like would just be looking at this and isn't in the context of our class. The letters mean something because they were defined in step 1 as labels in a picture. And it totally makes sense that their definitions are labels in a picture because honestly, that's what makes this physics, not just math. Because we're saying whatever we're doing in our mathematical computations in step 4 relate ultimately or refer to a phenomenon that's occurring in space and time. So we start right away with a diagram where all the labels in the diagram are actual letters that are going to be used later on. So so here's my diagram. I got K, I've got X equals 0, means the equilibrium position. X equals X naught is the initial position where the instantaneous speed of the object is 0. Okay, and the mass is m. So there aren't numbers in that picture. But this is why it's called diagram and fact pattern. Then underneath the it turns out that in this problem I was given numerical values for some of these letters. So okay, so I established them right here under the picture. K equals 200 newtons per meter. M equals 0.3 kilograms, etc. That's what I mean by fact pattern. Again, by the way, a lot of times in this class, or pretty soon, we're going to be solving situations where there just aren't any numbers, where we're just figuring things out in general. So it's another good reason to get in the habit of distinguishing the letters from the numbers right at the beginning. All right, so that's my step 1, diagram and fact pattern. Okay, now I go to the very first question and notice like just like in the homework assignment, the diagram came before even the first question because indeed that diagram is the situation to which all the questions will refer. So indeed, as people generally ask, when I get to question 2 or question 3 or question 4, for sure in step 1, I could just say step 1 for diagram, refer or see above. I could just say step 1 for diagram, see above. I don't have to keep drawing the diagram, but at the same time, I do have to do something like that. I have to address every step. Okay, so question 1. Also, sorry, pro tip. Maybe I already mentioned this. I'm telling you right now, homework 2 is a lot, which we don't get to for a little while because we spend time on this. But homework 2 is very mathematical. It's like math. It doesn't seem like physics homework 2. I don't present a diagram in the actual assignment for whatever reason. That does not mean that you don't. In fact, it's all the more reason that you need to. You need to start off homework 2 with a diagram, and you're going to have to come up with a diagram. Pro tip if you're listening right now, I highly recommend a cosine graph for homework 2. But make sure that everywhere in that cosine graph is some kind of label of some kind of letter that's going to be used later on in the problem. Pro tip, like omega is in the problem. It's involved in the problem. I won't understand what omega is unless somehow you make it clear as a label or something in reference to some kind of cosine graph. That's just advice for homework two, just to say that the diagram is always important, probably even more important when you have to come up with it on your own. Okay, back to this. Question one, you put in your own words, right? You don't copy and paste my question. You distill it down to its essence and show that you understand it. Certainly, symbols or mathematical equations are highly desirable. So question one is, in simple terms, at x equals x naught, what is f? F equals what? Or you could say at t equals 0, what is f? Same thing. So that's my step two, question two. I'm just looking at the chat if there's anything. No, there isn't. Okay, so we can go on. Okay, so this is all, again, question one of homework. So this is what I'm looking for. It's a lot, I know, but anyway, but it'll seem like, but again, most of you really did this. And let me say that again. I'm really impressed. I don't even know, like the first homework that I got from most of you in this class is like far more impressive than first homeworks in this class usually are. I don't know what that says or what's going on, but Quark bless you all. It means I shouldn't be wasting your time right now as much as I am. All right. Step three, Step three, GDP, general definitions and principles, right? This is where we're writing down what we know, but wait, we already wrote down what we know in step one, didn't we? Vashtistas, like what? Yaverbama, here's my point. In step one, we wrote down what we know about this particular problem, and then we asked what the question was of this. So step one was the situation, the particular situation, and then step two is like, what's the issue of the situation? What's the question it's posing? And then step three is, okay, what do we know about the universe before we even saw this problem? What do we know in general about space and time that we could apply to help us answer this question? So laws, definitions, principles, equations. So the key one that we need for this problem is Hooke's law for a spring, F equals negative kx. Okay, now here on the so I mean the GDP, the desired GDP for this problem is F equals negative kx. I'm providing a little bit more explanation than just that. How much explanation do I want from you? Well, okay, the rule of thumb is, first of all, you don't just present an equation out of nowhere. If it's the first time you're using an equation in like a document, you give it some context, give some explanation for that equation. Once you've explained it once and it's established, okay, then the rest of the document you can keep using it. But I do feel like some explanation is necessary, and particularly if it's something new, especially if it's something that you got off the web from the web or something, or like from Khan Academy or from a book. That's great. That's not cheating. But then if you just learned it on your own, you need to show that it makes sense and that you understand it and like why it even applies. Like just because something's true does not mean it makes sense. So, okay. So I tried to do that a little bit here. I'm saying like f equals negative, like what my handwriting says is any well-behaved spring will obey Hooke's law, f equals negative kx, for which x refers to displacement from equilibrium, k refers to the spring stiffness, and f refers to force. That's what I'm saying there. Okay, you could say something like that. Now, so that's like sufficient for your homework. I mean, something like that. But I'm going to turn the page. And this now, I mean, you could do this too. I mean, more is always, there's never any harm in explaining things more, especially if something is new or fuzzy in your mind. But the real reason I'm doing here on this page is for you guys, because you're coming from different classes, from different places. So I don't know exactly who knows exactly what. So this is my quick, like, this is me being a teacher for a moment. Imagine. This is my quick like explanation of f equals negative kx of Hooke's law. I also feel, I think, stop me if I'm wrong in the chat, but I think you did a lab last week, so I think you have some context for this. But what um, I think this is a definition of elasticity. I think Hooke's law is what it really means to be made of elastic material. To be made of elastic material means to be made of something that's springy, to be made of things that act like springs. What does it mean to act like a spring? It means that there's an equilibrium position. There's an orientation that the spring would sit in forever if you put it there. But the more you stretch the spring away from this equilibrium, the harder the spring pulls back, well, pulls or pushes to get to restore, to get the spring back to equilibrium position. So to pause for a second, like gravity also has an equilibrium position associated with it. Like the earth pulls objects down toward the center of the earth. Things, if you put them on the ground, would stay on the ground, right? So in that sense, gravity seemed the downward force of mg seems like it acts in that sense like a force that restores things to equilibrium, just like a spring does. But the fundamental difference that we're like deploying here is if you put something at a height of 3 meters, then the earth will pull down on it. Sorry, if you put a mass at a height of h, the earth will pull down on the mass with a force of mg, like the weight of the mass, right? You put a mass right here, the earth pulls down on it. It wants it to be on the ground. It pulls with a force of mg. But if you and that's very much like a spring pulls the edge of a spring toward the equilibrium position. But if you hold the mass at a higher place at 2 times h or 3 times h or whatever, the force exerted by the earth is still just mg, the weight of the object. In other words, the restoring force of gravity doesn't care. The restoring force of gravity tries to restore you to the ground or to the center of the earth, and it doesn't actually care how far away you are from the ground or from the center of the earth. I mean, within reason, as long as you're near the surface of the earth. But springs do. So the difference, so elasticity is a force that is actually dependent on displacement from equilibrium. The law that governs elasticity, Hooke's law, has an X in the expression, whereas the law of gravity, or at least near the surface of the earth, does not have a Y or an H or whatever in the expression. So that's part of the reason we study springs like right away in this class, or why we care about them in physics, is because they're our first encounter with a position dependent force. That's on the one hand. On the other hand, the dependence is as simple as it could get. It's not constancy, it is dependence, but it's as simple dependence as it gets, i.e., it's a linear function. It's directly proportional. If you double the displacement of the mass from equilibrium, then the force will double. It's that straightforward. Hence the graph here on this page. I'm just trying to summarize or review or whatever. The meaning of F equals negative kx is that the force exerted by a spring onto a mass is directly proportional to the mass's displacement from the equilibrium position. So the graph is a straight line. Why is it in the fourth quadrant? Because the graph is actually is a negative. Like if you hold the mass to the right of the equilibrium, the force will pull to the left. If you compress the spring in and hold the mass to the left of the equilibrium position, then the force will shove it back to the right. So that's what that negative sign is. That's why this graph has a negative slope. But slope, it's a straight line. Hooke's law is a straight line function. That's like my point right now. Straight line means constant slope. The slope is the rise over the run. In this case, rise is rise in force measured in newtons. Run is change in displacement measured in meters. So the slope of this graph is a ratio of like change in force. It's like how much extra force does the spring exert for each extra meter of displacement that you're asking it to undergo. So that slope, force per displacement, newtons per meter, is what we call K, right? I mean, F equals negative Kx is just like saying F equals mx plus b, only b is 0. K is the slope of that function mathematically. Physically, then, K is a measurement of how many extra newtons of force the spring is exerting for each meter of displacement that you're subjecting the spring to. So K is the strength or the stiffness of the spring. Again, this is, I think, review or boring for most of you, but and you looked at it in the lab. But to say that a spring has a K of 200 newtons per meter is to say that that K, no matter what you're doing to the spring, that K will be constant for that spring. That spring is that stiff. Another spring in the lab will have a different constant, maybe 50 newtons per meter, which means that other spring is looser, less stiff, won't pull as hard for every meter of displacement. But whatever spring stiffness is for that spring remains constant. It's and we ultimately call that, it's like a defining characteristic of the spring. We ultimately call it a parameter of the spring. So that's what K means. I'm still looking at the chat because there's nothing in the chat. Okay, so F equals negative Kx. K is the stiffness of the spring measured in newtons per meter. Okay, so all that was, again, that was just me talking. You don't have to say all that in your step 3, but that was step 3 GDP. So now we go to step 4. Now we go to step 4, particular application and work. So here's where you do like all the stuff. This, right? This is where you do the plugging and chugging. This is where you do the algebra. This is where you do the trigonometry, the calculus. This is where you show the work that most people think is work. And steps 1, 2, and 3 are like the setup for the work. Again, I'm going to reinforce, I'm going to repeat. Steps 1, 2, and 3. There's 3 of them before you even do the work. I promise you, that is actually the gift. That's super annoying right now. But to have 3 things that you can do to help you set up a hard physics problem is ultimately a gift once the physics gets hard enough. In fact, I'm going to take one more, but no, I won't. Okay, so here in step 4, you know you're transitioning to step 4. You know you've gone from what's generally true in the universe to what is particularly true in this situation. Or at least I know I'm transitioning that way because I generally start my step 4 by using the word here, like HERE, like comma. Like I'm saying here now, like we already know F equals negative Kx in general, but here I'm reminding myself, taking the information from step 1, K is 200 newtons per meter, X is 0.15 meters. Now I'm not repeating all of step 1. Like notice I didn't write the math. Like someone in the other class asked, like, wait, isn't this step 1 all over again? Well, a little bit overlaps, but no, it's not because I'm not putting all the information now in step 4. I'm just putting the information that I'm about to use that I'm about to plug in to what I said in step 3. So, okay, K here is 200, X is 0.15. So I plug them in. This is where I focus on units, do whatever I'm doing, stoichiometry, whatever you want to call it. I do canceling out my units and stuff like that. If there's scientific notation to worry about, this is where I worry about it. I do all the work here. Again, so this is where the work happens, step 4. Again, I'm going to say, I'm such a broken record. Um, can you imagine what I'm not saying, by the way? Yeah, I know. Neither can I. Uh, if step 1, 2, and 3 like annoy you and they bore you and you can't believe that I'm asking you to write steps 1, 2, I'm not saying that you do, but if you find it annoying that you have to write steps 1, 2, and 3 down even when you can already see the answer in your head, I also want you to realize this. I think again, I'm with you. I mean, I know I'm like being a used car salesman, but I can sympathize with how stupid step 1, 2, and 3 seem at this juncture. But another way to look at it is this. The reason step 1, 2, and 3 actually seem so stupid and annoying or boring is because you can do steps 1, 2, and 3 without even really understanding what the problem is asking, right? Like that's how generic they are, steps 1, 2, and 3. Like you literally don't have to think at all about what the problem is making you do or get to an answer just to write down. So that's why they seem boring. But that's the magic of them, is that those are things you can do before you really know what you need to do. And once you do those steps, they launch you organically into the things that you need to do. And you sort of never really have to have figured it out on your own. They help you figure out how to. So again, well, why do I keep saying this? Because my secret thing is to many of you who like did a great homework and got all these points and everything was neat and beautiful, but then you got to question 9 and then you were like, yeah, I like whatever. fair enough, except no. Like in question 9, all of you, even if you've never, even if you don't like calculus or whatever, you could certainly do steps 1, 2, and 3 for question 9. And you get points for that, right? This is how, for those of you I don't, that's how I'm scoring these things, whether it's homework or exams. Like I'm giving points for steps, not for correct answers. So it's just things that you're doing that will, okay, you get my point. All right, anyway. So step 4, so step 4, plug in, it's simple in this case. I plug in the 200, the 0.05. So now I get to step 5. Step 5 is my final answer circled. Notice two things about it. One, it is a complete thought, my final answer. It's not just like a fragment, it's not just like the number 30. It's a complete thought that when x equals x naught or equals 0.15 meters, then the force equals negative 30 newtons. Like that is my full answer. So notice number 1, it's a complete thought. Number 2, notice it totally refers directly back to step 2. It's like a closed conversation. Step 2 is a question. Step 5 is the answer. And anybody who wasn't in this class or didn't see the original assignment, if they know physics, could follow this, hopefully, and say whether they learned something from it or not, or say whether they thought it was right or wrong. All right, so that's question 1. That was a lot of nothing. I mean, there was a lot of a little. That's question 1. That's my answer. I'm going to pause for a second. And we'll start getting faster now. But first of all, any concerns or questions of any of on any of that on the physics or on the class or anything, like any concerns at all? I'm just looking in the. Are we good? We're Is that okay? We're good. We're good. Or so raise your hand, raise your electron. That's okay. Thank you, Gabrielle.
I kind
Okay.
of have a question,
Oh yeah, please. Yeah, I'm sorry. Yeah,
but
yeah, yeah.
it's more like it's not like directly related to the homework. It's more like a curious thing. I'm
Okay.
just thinking like, is there a limit to the displacement when using this equation? Because like if you think about it, like I don't know like how a spring behaves in reality because I haven't like played with it a lot. But you know how like when you compress like the spring to its like you know those like rainbow colored springs? Like when you put them in their most compact form, like they can't go any like denser or like shorter. So I was wondering like since you said like the equilibrium, like you can push the block like either way, like how do we determine like where like the limit to the maximum displacement is?
Oh yeah, no, that's a very good question. Okay, no, that's a very fair and good question. And for the and I'm totally going to answer. And also for those of you, anybody else, it's a it's actually a very good question. Period. Second of all, don't worry, we're not behind. Like we're already what am I trying to say? We're already ahead of where the other section is. So I don't want anybody to worry that you're losing something if I answer this question now. So yes, this goes back to right here where it said in step 3, I said a well-behaved spring will obey Hooke's law. So what the heck do I mean by that? Like, I mean, this is what you're getting at. Like because it's there's many things you could ask a spring to do that it won't do, or if it does them, it will do them, but then it won't obey this law. And for example, like what you're asking, what Annie's asking, like, yes, I'm making it sound like if you have a spring, you could extend it in one direction just exactly as far as you could compress it in the other. And what Annie's saying is that she feels like she's experienced springs that don't quite do that. Fair, I agree. And I'll even go for one step further and say, I bet Annie and other people in the room have even like played with things that like look like springs, like they're coils of something, maybe plastic, not metal, which already gets a little bit dicey, but that you've played with things that are coils, but they really probably don't like for example, if you pulled them in one direction, they started going back and forth, they wouldn't go back and forth forever the way the rest of the homework seems to imply that this thing would. So in general, what Andy's question is really asking is like why, like, like what's the threshold for why a spring would even really obey any of these descriptions versus a spring that is kind of springy, but doesn't really. Here is the answer. Here's the threshold. You could write this down or not. For a spring to be well behaved, for a spring really to kind of like obey all the math that we're about to say, first of all, the spring has to be really light, like very not massive. Com well, what does that mean? Compared to the mass that you put on the edge of it. Like, and then what, like all these things you notice, we have a mass at the edge of the spring, and we're using that mass to focus our attention and track all of the motions back and forth. This actually not just it's actually crucial to the whole situation. Just like in lab, you had a mass at the end of a spring. It's crucial that the mass that we're tracking, that it has a mass that obeys F equals ma and all those other things, but that its mass is so massive that when you put its mass on a like inertial balance or a digital scale or whatever, it registers some number like you did in lab. If you then put the spring for things really to be good, and what I'm about to say might not have even been true in your lab, if you then put the spring on the same digital balance as the mass itself, the spring should be so light that on that digital balance that you used for the mass, the spring comes up as zero. That's very important. In other words, there's no, and I'm going to say more about this because really it is a great question. And again, I don't know why I'm so defensive today. Maybe I'm always defensive because this question Annie's asking, like, even if you might be thinking, well, do I really care about springs this much to talk about them for 20 minutes? It's not just about springs. It's about how physics works in general. Like, we have these idealizations that make it seem like things have to be perfect for any of this to be true. But things don't have to be perfect, but they have to be very good. What does very good mean? The first thing is that the spring that Annie was picturing when she asked the question, like, what about these big rainbow, like plastic springs that you could sort of pull out, but you can't push back in? Yeah, those springs are not great. They're fun, but they're not really going to be used in the lab and really demonstrate all of these things. First and foremost, because they're too heavy, is the part of what I'm saying. Those springs themselves have mass. We're really talking about here about a spring that exerts forces onto masses, but itself doesn't really receive forces. Again, there's no spring in the world that has no mass. But if you get a spring that's light enough compared to the mass that you put on it, light enough that it won't register a number on the same scale, then we're starting to be in business. That's qualification number one. Qualification two, also related to Annie's question, I mean, definitely related to Annie's question, is for every spring, no matter how light it is, there's a certain point if you ask it to compress too much, or even you ask it to extend too much, it'll eventually first start violating Hooke's law. Like it'll start exerting forces that are like quadratic function of position rather than a linear function of position or whatever, and then it'll break. So like where is that threshold? And they might like do the same thing even more extremely in the compression direction, like what Andy's asking. What's the threshold for that? It's this. All of these things assume that the displacement that you're asking the edge of the spring to undergo, like this is like literally the answer to like literally what Andy was asking. You springs, even when they're good springs, you all of this stuff applies only if the displacement of the edge of the spring in either direction, compression or extension, if the displacement is really small compared to the size of the spring itself. What do I mean by really small? Sounds vague, but it's not vague. It means whatever meter stick you used, or micrometer or electron microscope, whatever you used to measure the length of the spring itself, if you then started measuring the displacements of the edge of the spring, the X value, it would be between the cracks of the meter stick you used to measure the spring itself. Like zero, it would show up as zero on the same meter stick. Um, those are the two main. So that's a very, and do I want to say what was that? But that's the main thing. I mean, let me back. So that's a very long answer, of course. But the main thing I'm saying to Annie is right. Those big plastic springs that are rainbows. I mean, I love them. Who doesn't love them? My children love. But yeah, they are too massive often, and to, and when you're asked, they're too massive, and when you're asking them to displace, they do compress more than you'd expect. They do actually compress more than it looks like, but no spring will ever compress or extend a significant amount compared to its length without it starting to violate Hooke's law. Okay, that was very, does that make any sense at all?
Um, yeah, I guess it makes sense. So can I just like kind of like summarize it and you
Yeah,
tell me
yeah,
if you
yeah, yeah,
get
yeah,
the
yeah.
so you're saying that like basically there is no like universal bound for delta X, like for displacement, so long as like the displacement is small enough that the spring does not like undergo some sort of like deformation or it gets compressed so much it doesn't like behave as it's supposed to. Is that what you're saying? And then we
Yeah.
also assume the spring is um weightless and again by ratio like to the mass that it is attached to.
Yeah, yes. So yes, that is what I'm saying. And to summarize the summary, right? There's no universal bound, like you say, on the displacement amount, but there is a comparative bound. The displacement amount always has to be negligibly small compared to the length of the whole spring, which you just said. So yeah, the, right. Does that make sense? Right. Okay. And everybody else. Okay, it's 4:02. We still have 18 minutes. And honestly, we are right at the. I'm gonna do more. I'm gonna do more. I don't know. I really am defensive today. I feel like I'm trying to sell everybody a used car. What is the deal? Um. Well, I think maybe it's because like I know how boring it is to walk through the 5-step method. I don't know, but I will get back to answers in a second. But I also, again, I want you guys to know that exactly where the other section ended today was like here. So you're not behind at all. And I just and here's the thing in terms of being a used car salesman or defensive, like the reason I really like Annie's question, it get just in general, just as my little plug for physics, because it bothered me for so long. Anytime we say in physics, oh, pretend physics is negligible. No, we don't say that. I mean, pretend friction can be neglected or something, right? Whenever we say like, oh, friction is so small that we can ignore it, or the displacement of the mass is so small that we can ignore it. I just want to say, I know at least the first 400,000 times I heard that in high school, in college, in grad school, when I would ever hear, like, we ignore the friction, I totally thought, I thought many things. But one of the things I thought in the beginning was like, well, that's ridiculous. I mean, I thought I'm taking a science class. Like, isn't this supposed to be about the real world? Like, I thought this would be the class where I get to learn about friction or whatever. Like, why do they keep saying friction can be ignored or something? And then even when I got a little bit more advanced, or I sort of bought in, or I got used to it, or I accepted it, whatever, then what would go through my mind when people would say, like, the displacement is so small that you can ignore it. Then when I thought in my mind was, okay, I know what they mean. We're like being ideal, like we're like being in a math class, like a Euclidean plane has 2 dimensions, but it's like so super flat that it's so super thin in the third dimension that like you can ignore the third dimension. But it's just, but I thought, well, it's like a math class. It's just all in my mind. These are idealizations that exist in the mind that are fascinating, but they're not like they don't exist in the real world. But I want to say, like, no, this is a science class, not a math class. It can seem very theoretical. We're going to do all of this math. It can seem very abstract and theoretical, but I want to tell all of you, and it took me years to realize this. This is science, not math. And when we say a well behaved spring or something, we're not just saying a spring in our mind. We are talking about a spring that could exist in the lab. And when we say you can't make the displacements too large, we always actually mean you can't make the displacements too large in comparison to something else. And we always actually mean, when we say in comparison to something else, we always mean that whatever one measuring tool you would use for one thing wouldn't work for the other thing. Like that is a concrete, real standard that actually is a measurement standard. And that's what actually makes it science, not math. Like, and so put one final way, and then I will move on. What we're really saying is, of course, no spring is perfect. No spring is perfect, but some springs are good enough to meet the measurement standards that we're talking about. And they're good enough, therefore, to do lab exercises, which doesn't mean our lab exercises always work out perfectly, but it means they're good enough to do experiments and learn things with. And then they're good enough to build machines with, and the machines work, right? This is about reality in the end. It's not just about our minds. Just saying. All right. But that's no, okay. That's it. Okay. So what I'm going to do now to get our money's worth a little bit. Whoa, hello. Right now I'm just going to write down some answers so that so I can speed up a little bit and like wake us back up. So I'm going to write down. So this is not what you would do for me. You do out the whole 5-step method or wherever corrections I asked you to do. But if you want to see answers, just so you can know if you're doing it right or whatever, here's some answers. Again, this is just like so you can check yourself or whatever. And I'm really being abbreviated. Like really technically, I should say like at x equals x naught, a equals negative, etc. But I'm just not even doing that because I just whatever I want. Yeah. Same question. Oh. That's supposed to be an infinity symbol. Okay. I'm gonna pause there. So 8 and 9 is where things get sort of interesting. I mean, whatever. I'm not gonna well, actually I will. All right. I will actually. I'll give all the rest of the answers. It's 408. Tell me if you want me to scroll back. But these are just the answers. This again is not. We have to talk about them. But question 8 is Sorry, 1 second. Sorry. Okay, and question 9, I'll say the answer. Obviously, it's going to take us a little while to get here, but I believe the answer is this. This is correct, but I'm gonna rewrite it so it fits. Hold on, sorry. Okay. Now, we have 9 minutes. Again, this is not the work. These are not explanations. I'm not pretending that I just taught you anything. And I'm also not saying, like, and if you just wrote this for me, like, I don't think that's good enough. I mean, it's not good enough in either direction, but it's just like a checkpoint. It's like a checkpoint. So you can know, like, if you're on the right page or not so far. Um, yeah. And so because questions one, two, and three, oh, I'll leave it in questions. Notice right on the first page of today's notes, like in questions one, two, and three, I think the GDPs that you would be using are F equals negative KX and Newton's second law, F net equals MA. Like I think those are sufficient to do questions one, two, and three. Then when you get to questions four and five, you have to shift your thought process, as many of you did, as maybe all of you did. And forces and accelerations are no longer a sufficient way to think about the question because, as you find in question four and five, the force being exerted and therefore the acceleration is not constant from one place to the next. So once it's starting to ask about speed at any given position, all of our old kinematics equations, all of our old constant acceleration equations from the beginning of physics 203, like they don't apply anymore, right? So I guess a quick summary here is, so when you get to question four and five, if you look at question four and five are asking you for what I would call a speed spot um, correspondence, right? Like question four is saying at this certain spot, what is the instantaneous speed? And then question five is saying when it has this certain instantaneous speed, what spot is it at? Spot meaning like position in space, right? My suggestion to everybody is once ever in physics, anytime anybody's asking you about a correspondence between where something is, a particular point in space versus how fast it's going, or it's asking you to compare one spot in space to another spot in space and the speeds at those two spots, that is asking you to consider work and energy concepts. That's what the work and energy concepts are for. When forces are not constant from one spot in space to another, but we're still wanting to know about how the motion is evolving from one spot in space to another. That's exactly where we use work and energy because, so this is like a quick, I'm just, again, this is like technically a review from last semester, but I'm just, because work is the accumulated effect of force through space, through a distance. So when forces are changing from one spot to another, that's when we use work and energy to solve problems. So the mathematical statement that you'll eventually arrive at as your GDP for question four and five is a mathematical expression of work and energy transfer, or what you might call energy conservation. I mean, I'll explain it more in our next class, but that's what you need for steps four and five. Um, then and then question nine goes in a new direction. So I actually that's I think all the information I feel like I need to provide. Right. So these are the answers. Oh, one last thing. In question nine, again, everybody, it's really all about question nine, me trying to build to question nine. And everybody's at I mean, your answers to question nine across the board, your responses were more varied from one to the next than like to any other question. Like most of what you guys did for most of the questions were pretty similar, which is great. And again, the work was great. I mean, I'm really impressed. Question nine is where I could see people are coming from different math classes or different institutions or different websites. And that's all fine. Um, uh, but I will say, even those of you in question 9 who kind of did feel like you knew what you were doing, and even if I said, but you need to explain this more, even if you feel like you know what you're doing, often people were doing things in question 9 that might even have been correct, but then in the final moment, they didn't get this answer. Sorry, this answer, 0.116. And that may very well be because your calculator was in degree mode rather than radian mode. I will say that by the time we get to question 9, once we talk it through, when we see it, you're going to see that almost any method you do, you actually are going to want your calculator to be in radian mode. So if you're wondering, if you think you did all right, and you can't imagine why you did, like check that. That might be why you might have gotten a different answer, like 0.135 or something like that. So this never happens to me, but it's a little bit early. But so we have like, so are there any questions? Are there any questions of any kind at all? At any of any kind? Oh yeah, okay, Andy. Yes, 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 absolutely.
Yeah, so I was looking at the answers for 8, Q8. You said magnitude, right? But um I think for my like homework, I didn't like do magnitude. I did like I considered the sign as well. But then like for jerk, is it supposed to be an increase in magnitude or decrease? Because like ultimately I derived the function for jerk to be some constant times velocity, right?
Right, right. Okay, good.
And
Yeah,
oh wait, yeah. And then like wait, let me see what I did. So it's a oh, never mind then. I think I did something wrong.
okay, no, but that was good. Fine. But yes, the thing you just said is that's great that you did that. But yes, that would I think lead to my answer. Not, but yeah, I think you just answered your own question. But yeah, 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 yeah. Okay,
Yeah,
good
sorry.
talk.
But
Okay,
oh yeah, one more question. So like for the formula for jerk, we when we're plugging in values for lo velocity, we have to consider like the sign, right? So we cannot just put like whatever constant times 3.87. We have to do times negative 3.87. Is that right?
yeah. Okay, good, good, good question. Like when you're putting in the values, yes, you would have to put them in with their sign. But then, and yes, analyze it like that. Yes. But then at the end of the day, the question is asking, so what's happening to the magnitude? So once you look at your final thing, then you don't take into account the negative sign. Like, so the simple example being just with the velocity itself, like right at the beginning, its velocity 0, then it at the equilibrium position, yes, I agree with you that its velocity is like negative 3.87. But if the question is just asking what happened to its magnitude went from 0 to the absolute value of negative. Like the what happened to the magnitude is it went up from 0 to 3.87. If I had actually asked what happens to the value of the velocity, then the answer would be down. But since I'm asking what happened to the magnitude, I think the answer is up. Does that make is that
Yeah, yeah, that makes sense. I mean,
okay?
thank you.
All right, cool. All right, cool. All right, so that's actually okay. So let me know if you have any questions or issues or blah 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 blah. But other than that, I will see you all. I mean, I'll hang out for a minute. I won't go until the last of you goes in case there's issues. But other than that, you have a nice day, and I will see you Wednesday. All of you. Yes, have a good night. Yes, thank you. Okay.
Thank you. Have a good
Thank you.
one.
You too.
Thank
Thank
you.
you. Thank you.